Hello and welcome to our webinar covering tips and best practices around strain and force transducers for universal testing machines. Thank you so much for being here. I'm Nick Erickson, your host for this webinar. Today I'm joined by Dan Raynor, the Force and Strain Product Manager at Instron. In this role, Dan oversees our load cells and extensometers. He's been with Instron for over 18 years, serving in a wide range of capacities, including technical support, manager of our applications lab. And he also spent over 7 years working with our dynamic testing equipment before stepping into his current role. We expect the presentation should take around 45 minutes, which should leave us plenty of time for questions at the end. These can be submitted at any time using the questions pane in GoToWebinar. I also want to mention that we are recording the session. All of you will receive an email afterwards with a link to the video, and it'll also be available on our website, instron.com. So with that said, I'll turn things over to Dan to get us started.
Hi, welcome everyone. Thanks, Nick, for that inspiring intro. It always surprises me to hear how long I've been part of materials testing, because I feel like I'm always learning new things. So let's get into it. So here's the agenda for today. Little worried that we may have oversold some people's expectations based on the title, but basically this is what we'll be presenting. And we're going to be answering some of the most common questions that we get. So much of this is related to the Bluehill Universal software, which means almost everything can be found in the help file if you need more detail or still have questions. This webinar does assume some basic understanding of strain and force. So just to start with, strain or elongation is being the change in specimen length relative to the initial length of the specimen. So it's unitless. It's usually represented as a percentage or change per unit length. Again, we're going to be using Bluehill Universal, but all of this is the same for Bluehill 3 as well. So you can see we're going to start with some terminology for strain and displacement in the software. We're going to show you how to compare different strain measurements. We're also going to talk about setting up a transverse strain measurement. We're going to show you some things you can do with the Pretest Limits for measurements, and also get into transducer ranges, whether that's load cells or extensometers, and then finally some data rate settings that you may not be aware of. So we'll start by making sure everyone understands kind of the most basic fundamental terminology. So these are the strain 1 and strain 2, and these are most often from a strain gauge extensometer, as you see from the clip-on extensometer shown here. And these are they're physical transducers or extensometers, and they would be bringing in the direct strain or displacement measurement. And we use the strain 1 and strain 2 connectors on the controller. So this is an image from our latest 34 or 68 series frames. They've got 2 connections here. They're optional. And they're right next to where the load cell would plug in for force measurement. So we can bring in these strain 1 and strain 2 are typically analog signals from a strain gauge, but also we can essentially bring in and record any 0 to 10 volt signal. We can also bring in digital strain, and that's brought in by the encoder connection you see here. And again, the encoder connection is on our latest 34 and 68 frames. Previously, we had different ways of bringing that in. So we also have what we call tensile strain, and this builds on that basic strain input, and it provides some additional capabilities. So it's considered a virtual measurement in Bluehill Universal. It works in a couple different ways depending on what the source of your strain measurement is. So as mentioned, it's taken from your strain or displacement source. It can either be directly from an extensometer, in which case tensile strain would be the same as strain 1, or it can be calculated from something like your crosshead displacement. So if you didn't have an extensometer, your tensile strain can be calculated based on the displacement and the original, the length that you entered for the specimen. This also happens to be the source for tensile displacement, which we'll get into in a little bit. And also, we have terms like, sorry, for the composite strain measurement, we're going to talk more about that later, but that really is when it, yeah, we'll talk about that later. But we also have terms like compressive strain and flexure strain, and they're very similar to tensile strain, but they're really most used in the more appropriate test methods for compression or flexure. For example, compressive strain just happens to be positive in the compressive direction. So this way everything agrees with each other during the test and looks good for graphing and results. And 4-point flex is a little different. As you can see in this image, during a 4-point flex test, the specimen actually deflects more than the upper loading anvils would move due to the curvature of the specimen. So in order to measure that distance in the middle of the specimen, either with an extensometer or without, there's basically an equation that it follows depending on the specimen thickness and the span ratio between the loading and the support anvils to calculate what that point would be. So moving to displacement terms, they're all kind of related, but displacement in Bluehill Universal is the distance traveled by the crosshead itself. So this is measured directly by an encoder. You can't balance it during the test, but you can balance or zero it before the test starts. And so this would always be basically an absolute value as it's running. And when it's zeroed, that's typically referred to as the gauge length. And so when you're running a test, you might want to return to gauge length, and that's what this reference point would be good for. So you can finish one test, return to gauge length, and start the next test. We also have the term, and so this is this is an image of the handset, and this is showing the soft keys can be programmed typically to balance the load cell or maybe an extensometer, but we also have a built-in button for balancing the gauge length itself. And then moving to the term tensile displacement, similar to the tensile strain term that we had for strain related, this is calculated from tensile strain. And we can get into that a little bit, but basically the idea is that if you're using an extensometer, tensile strain will be the same as strain 1, for example. And then tensile displacement, you're essentially taking tensile strain, multiplying it by the gauge length, and getting a displacement value. So now you've got units of millimeters or length within the gauge length of the extensometer on the specimen. But if you're using crosshead displacement, your tensile strain would be calculated from your crosshead displacement relative to the initial length of the specimen. And then tensile displacement would essentially be back calculated to crosshead displacement. So it can be a little confusing, but that's why we're going to show you in a little bit how it would look on a graph in Bluehill. This displacement, again, would be within that length of the specimen. This can be auto-balanced at the start of the test, so it starts at 0 every time, which is very nice for graphing and for calculations and just different reference points. So in that sense, it is different than displacement from the moving crosshead by itself. And this is also a composite measurement, like we mentioned tensile strain was. And again, we're going to talk about that a little bit more soon. And I know these terms seem simple enough, but they really play a big role in how they're treated in Bluehill Universal and how they behave with things like other features like expression builder, different calculations, compliance correction, graphing domains or calculation domains, auto balance criteria, end of test criteria. They kind of far reaching. So we just want to make sure that the building blocks are in place. And then we also have things like compressive and flexure displacement. Again, similar to the same ones for strain, they would be positive in the compressive direction, and they would be units of length instead of strain. And as promised, what is composite strain? So this is the term that Bluehill U uses when you're transitioning from one strain source to another, typically from an extensometer. that maybe can only go up to 10%, and then you have to remove it during the test. So your specimen can continue testing, at which point we transition to crosshead displacement by default. And so it becomes a composite measurement. So we had two different sources essentially during the test. There is an extensometer removal correction algorithm that ensures a smooth transition, and it does that by looking at the point itself where the extensometer is removed and what the crosshead had done so far and what your initial specimen length was, and it smooths that transition, and it works very well, and it should give you a nice clean line to continue on getting your strain measurement essentially from your crosshead displacement. And if we look, if we look at this graph, it's a good example of why you need to choose the correct measurement when you're setting up calculations. For example, this blue line is your clip-on extensometer. It was removed when it reached 10% strain. That's why it just flatlines, because it stopped recording essentially. And then your green line is the tensile strain. And so that followed the blue line exactly, because the blue line was the source for tensile strain up until this removal point. And now the green line has transitioned to crosshead displacement. And if we look at the brown line here is tensile displacement. And again, that was from tensile strain the whole time. And your red line is your crosshead displacement. So it's very linear, and it's almost essentially parallel to your tensile displacement. But that's the source that's being used for this green line after the blue has been disconnected from the specimen. And also same for tensile displacement, since it's based on tensile strain, making sure it's the right source for your calculations and everything else that it might affect. And so we're gonna get into very soon. We'll go to Bluehill in a moment, but when you're comparing different measurements in Bluehill Universal, graphically is the best way for me, I think. And so things to think about is, when did that source transition occur? What measurements would start at 0 or not? And when are measurements the same, such as when strain 1 is your strain source for tensile strain, they would be the same number. As well as if crosshead is your source throughout the entire test, your tensile displacement will be the same as crosshead. But as I mentioned, you can balance it to 0 and do other things with it. There's also a raw data viewer for those that prefer numbers over lines on a graph, and we'll show you how to add measurements to that. And also there's a data point selector that is very useful on the graphs. And we'll also show you some test cam video and how it synchronizes with those. So with that said, we'll jump to Bluehill Universal. Make sure this works. Okay. So we've got our test open. And so this is the graph that I was just showing you on the slides. And so we know we can make it larger. One thing we're going to do is we right click and enable data point selector. And so now we can click on any one of these spots. If I select specimen 1, so all this data, all these curves are from one specimen. And so now that we selected it off to the side over here, we can actually click on different data points. And so each point I click on is a different data point. And you'll notice that, you'll notice that if I click on one graph, it shows up on the other one as well. So if I click over here around 10%, it shows that this is the removal point for the extensometer. And also, if I look at the raw data viewer, when I clicked on that point on the graph, it highlighted the data point in the test. And from there, I can see all of the raw data measurements that we had been recording. So time, displacement, and force are the standard ones. and I've added some tensile strain and, in this case, digital strain, as well as displacements. So I'll move that back out of the way. See if I can get both of these at the same time, so that as I click on this, you see the number in the raw data viewer change. So right now I'm on data point 345. If I click later in the test, it's 3049. And also you might notice that in the test cam window over here, it picks the frame of video that's most closely synchronized with that data point. So in this case, we're not recording, hundreds of data points per second. We're collecting, I think, 10 frames of video per second in this case. And we could just play the video and watch it. It's not too exciting throughout the test, but by going from the beginning of the test where you can see the specimen, and then later in the test, you could see it's actually strain whitened. So the color of the specimen has changed. There's a reddish tint there because we're using our AVE2, the advanced video extensometer, and that has a red light for illuminating the specimen. That's also where these 4 white marks on the specimen come from. So we're tracking these marks in real time. 2 are for axial strain and 2 are for transverse. Which brings us to, we'll jump over to the measurements of the test method. And you can see we've got, it won't let us move them over because we already ran some specimens. We're gonna get out of this in a moment and show you some other stuff, but the idea here is you've got physical measurements up top and then virtual measurements on the bottom portion. We've got our tensile strain source is set to our digital strain axial. There's multiple places to do that. And then, of course, we have got tensile displacement and so on. You'll see for this digital strain 1 is our axial, digital strain 2 is transverse. We're going to talk a bit about transverse in a moment, so I'll try not to jump ahead there. But the idea is that if you had multiple extensometers, you would move over different strain measurements. So you would just add them to this available list, and you would tell them where they're connected, and then you can use them for multiple other things, as well as the source for your strain measurement. So if we go to test control, for example, and then the strain window, this is the primary source selected. So it's digital strain 1 because it's a digital extensometer. And also we have it set up to remove the extensometer during the test. Now, physically you don't have to because it's a non-contacting extensometer, but I just wanted to show you how the data would change when your sources change during the test. And so in this case, we removed axial and transverse at 10% travel. So we're going to go back to the slides now. Share the right one with you. So moving on to transverse strain, which is obviously very similar to axial strain, but it does take a couple more things to set up in the Bluehill software. Partly because we made it we made Bluehill very powerful, but and in that sense, it's got some kind of universal capabilities that fundamentally make sense. Sometimes and we tried to make it easy enough to use and not get too cluttered. So by making it very universal, you don't have many different, rigid structures that you need to choose or work around. And I'll show you when we're creating a transverse strain measurement. The challenge is that transverse extensometers don't have a fixed gauge width because you never know what width the specimen will be. For an axial extensometer, it's easy to define a 25 millimeter or 50 millimeter or any of that because your specimen can always be longer than that. But if you're measuring transverse, you want to actually contact the edges of the specimen. And no matter how we try, our specimens might be molded or cut to slightly different dimensions. And that's why we measure them. So in that case, we would actually use that measurement as your gauge width in the measurement of Bluehill Universal in the software. And what you're seeing here, this is an example of one of our biaxial clip-on extensometers. So there's 2 axial measurements, one on each side, and then the transverse would be across the width. And this red arrow demonstrates the range of adjustment that we can make for our transverse gauge width. So we would move this part of it anywhere along this red arrow, and that would set it for the different gauge widths of the specimen. So there's a big range there. It's very flexible. So we're going to show you how to set it up as a virtual measurement in a little bit. Also, some digital extensometers need an extra step. And it brings us to Expression Builder as well, which we're going to touch on a little bit, but we do have next month, I think we have a webinar that's going to go much deeper into Expression Builder and variables and how powerful that can be. So another aspect is pretest limits for different measurements. I would say the most typical one is around force, and that's what we're showing here, is so that any measurement, really, not just physical, will have this little checkbox for pretest limits, and you can enable that, and then you can set your limits for a minimum and maximum. They don't both have to be positive. The minimum could be negative, so it could be plus or minus 10 newtons. In this case, I'm showing an example between 8 and 10 newtons. The idea is that this would prevent the test from starting if it's outside these acceptable limits. And so, for example, a test standard might say that you should start your tests somewhere below 10% of your expected yield strength. Now, we do have a preload feature, which is really just to get any kind of slack or tension out of the load string or out of the specimen gripping. But it doesn't unload it. So if I told my preload to go to 10 or 15 newtons, if I was somewhere above that at say 16 or 20 newtons for some reason, it would just see that it met the requirements of 15 newtons and start the test, even though it's at 20 newtons. In this case, this pretest limit would prevent it from starting unless it was, in this case, between 8 and 10 newtons. So they can be useful for many scenarios. They can be found in all the measurements, and really it's whatever fits your application, how useful this might be. And so let's jump back to Bluehill for a moment. So like I said, we'll go back to measurements, and I'll take force. And so this is where we can enable the pretest limits. And again, you can type in any numbers you want. You can change the units as well. So in this case, they're all force units, but anywhere from kips to newtons. You got a big range there. And then, yeah. One right before this, when we were talking about, I mentioned Expression Builder. So in Transverse Strain also, so this is where it asks for a strain source and then your gauge width. And in this case, we've got our digital strain as a source, and our transverse strain gauge width typically is direct from the extensometer. It would measure it, and it would actually use that measurement as the strain source or as the gauge width. In this case, we wanted to use the actual width of the specimen. Let me actually get out of here for a moment. Let's save changes. And so we're going to show you that if you start a new method, it'll allow you to choose some things. And so when we select a new measurement, we'll have options and show you where that expression builder lets you choose the gauge width. Measurements, and see we'll expand the virtual measurements. Actually, we'll move over strain 1 for a moment, and then transverse strain, just like that. And so now we'll use our source as strain 1, and it's only in this drop-down list because I just moved it over to the available list. If it wasn't there, it wouldn't show anything, so it doesn't clutter up the drop-down lists with things you don't have enabled. And then looking at this transverse strain gauge width, you can see we've got the number pad here, but then you also have this function button, and this is Expression Builder. So instead of just typing in a number or a fixed gauge width, we can actually use variables. In this case, we've got a list of variables on the side. We'll go to specimen properties and we'll select width. And so now this is a variable. We'll select OK. And so now it's going to go to the specimen screen, the properties and specimen width. And whatever width this is, it'll use that for that particular specimen. In this case, the default value is set for 10, but for each specimen, we can have an operator inputs, and we can put in, 10.01, 10.07, 9.99. Just those small changes can have an effect on your strain measurement. And so that's just one example of what Expression Builder can do. Again, it's kind of throughout Bluehill, whether it's different domains for your graph, different domains for your calculations, or just using variables in different ways. It adds a lot of flexibility because it can be, now you've got something that's dependent upon other inputs. It's not just rigid and fixed. And when I say other inputs, we can also have sample or specimen inputs, and those are number inputs from the operator. We can also we can assign units to these, so they can be in not just numbers, but units of length or force or anything really. It's a huge list. And then choice inputs is a whole nother thing, which maybe for a few, I'm sure we've done it before in past webinars, but we'll probably do it again. So moving to the next one, let's see if we can get there. So one of the, a significant number of questions we get from people are load range accuracy, whether that's tied to what forces can my load cell measure accurately, or my extensometer, any kind of transducer. It also ties to how or what ASTM or ISO standard were you following to have it verified, and then what your application is. So this in itself was a whole series of webinars. We did 3 webinars in the past couple of years from our calibration lab experts regarding calibration and verification of load cells. So we're not going to get too deep into this. There's a lot of nuances and metrological aspects to consider. But for the most part, Instron, for example, on our latest 68 series frames, the measurement accuracy, if you're using our 2580 load cells, and if you have our advanced performance option for Bluehill, we can measure with an accuracy, I use that word, or error of your measurement error, plus or minus 0.5% of your measurement down to 1/1000th of your load cell capacity. So if I had a 1,000 Newton load cell and could measure down to 1 Newton with an error of plus or minus 0.5% of 1 Newton. So again, that is what we guarantee you can measure. Not all load cells are made the same, so if you're using another load cell in our system, that's all part of the whole load weighing system, whether it's the transducer, the load cell, or the electronics. There's analog to digital conversion that happens, so that's all part of it as well. And the idea is to get a nice clean signal without a lot of noise, and actually getting the correct true measurement. And so part of the questions also are, what happens if I measure outside my load cell's accurate range? I know I've heard some people recently still talking about, well, as a general rule of thumb, transducers are linear in the 20 to 80% range, and you shouldn't use anything outside of that. I think we can officially put that to bed. We can go down to 1/1000th of capacity all the way up to 100% of load cell capacity. And you can do that all day, every day. So there's no reason to not use the bottom 20% or the top 20%. You can use the full range. It's all very linear. There's a lot of other aspects of load cells and measurement that we consider, but certainly you can use the full breadth of the load cell capacity. The crux of it is probably more so around what it was verified to, and the range that it's verified is chosen by the user and what's best for your application. not so much by the person doing the verification or that the accredited group. So for example, Instron service engineers would come to your site, verify your load cell. Typically we start down at 1%, but it could be higher than that if you don't plan on using it. You just need to be aware that if you're doing testing below the verified range, you're most likely not meeting, if you're following a standard, you're not meeting the standard requirements. For example, ASTM standards typically refer to E4 for load verification, and ISO is 7500-1, and they explain the process and how it should be done. And then the output of one of our trained engineers doing that is that we're also accredited to give you a document stating that it's been calibrated compared to a known standard, and here's the documentation. And again, we've got several webinars that go deep into this type of area that would probably be very interesting to many of you, and I recommend those. Just making sure I'm not missing anything else I wanted to mention. And then historically, some years ago, some people would ask, how can I change my accuracy range? And that ties back to years ago. We had, due to the, I guess, limitations of technology, perhaps, in order to get a accurate measurement over a known range, we would have kind of different ranges that you could set your load cell up for, and whether that's, the bottom 20%, the middle 20%, the top 20%, something like that. Nowadays, with the technology we have and the design of the load cells, as well as the analog to digital conversion and the other kind of standard, industry standard algorithms that we use, the oversampling, things like that, to eliminate as much noise as possible but still get the correct measurement. We don't need to do that. We can use the full range of any load cell as soon as it's plugged in. And you can see here, so some other things we can do also is the periodic calibration reminder. So this is in the transducer settings window. So this is where you would normally, you would calibrate it. There's a button called checks. And so that would allow you to enable periodic calibration, in which case you can give it a time interval, say every 30 days, or once a year, usually 6 months maybe. It would remind you that it has to be calibrated. But this can also be used for just your operator in the lab, that, hey, every 30 days we want you to calibrate the load cell, or every morning perhaps. Then it can also do a balance drift check. And so that is looking for, if you balance it and it goes to 0, how long does it stay close to 0? This would be a good indication if there was damage, if it was overloaded, the load cell might drift away from 0. And if it does that within a short time interval, it may be time to get that checked out or re-verified, or just make sure that it's not affecting your test data. Most static tests are a short enough time period where the drift wouldn't significantly affect it. But again, depending on the application, how important that is. But this is where you could set that up. And then finally, setting the proper data rate. So we do have a previous webinar, and we also did an Instron Live devoted solely to data collection. Again, this is a much bigger topic perhaps than I would fit into one slide or even this webinar. But the idea is that your data collection should be driven by your application. And the intent is to be able to catch the peaks. Those are both maximum and minimum. And of course, peel testing is a great example, as many small peaks that you don't want to smooth out, and you don't want to just record all the noise either. And you don't want so much data that it's unusable or unwieldy to export or do anything else you might be doing with it. We can collect data up to 5 kilohertz with the advanced performance option. That should be plenty for anyone. The idea is to catch very fast events also. Again, there's more to data rate than just how many points per second you're catching. So we'll just kind of touch on it here, but the idea is that if this is my curve, say from a peel test or any kind of test, really, my data rate is set for time, and this is the frequency of it, so every line would be capturing data. And so all of the stars shown would be a data point. And at that point, I would collect, well, I'd record what the time was. I would collect load, displacement, maybe strain, any other transducer I have connected. And if I connect those stars, I get the red line. And the red line, I think we'd all agree, is not a good replacement or indication of what was actually happening. So this is a good indication of not enough data points. We probably need 10 times as many data points here to redraw that black curve correctly. And so this is just what to watch out for, that if you are collecting data and it looks perfectly smooth every time, or if every test is right on top of each other, just think about, is my data rate having an effect here? Should I be collecting more data, see if anything changes? Also, if you see sharp changes in the curve, as you see with this red line, that's a good indication of not enough data. Most things in reality aren't that sharp and direct. There's usually somewhat of a curve or a change in direction if you're seeing this type of behavior. So that sharpness in the curve would indicate not enough data points. And let me show you where that is in Bluehill. And so if we go to test control and then data, and so now we've got multiple criteria you can see here. If we go up here and change default, change it to custom, we can have up to 3 different criteria for data collection, and they're all working independently. So whichever is met, it will collect a data point. In this case, we're looking for the interval of 20 milliseconds. So this is every 20 milliseconds or 50 times per second, it would collect the data, and it will collect all of the data from all the transducers, all the measurements. So not just time, but load, displacement, strain 1, things like that, as well as every 1,500 newtons change in force, it'll collect a data point. And then we can also say based on displacement, so maybe every 1 millimeter. One of the good examples of this is during a creep test, where you've got a constant force applied to the specimen, and you're looking to see how the displacement changes. Well, if my force isn't changing, that wouldn't really be a good criteria to set for my data collection. And this is a very long-term test, so I wouldn't want 50 or 100 points per second. I don't even need 1 point every second. But maybe I would look at, see when my displacement changes by 1/10 of a millimeter, record a data point. And just for good measure, maybe once a minute, record a data point. So I would have those 2 criteria set up, and that would give me the right amount of data for my application. And I'll just show you where that the load cell settings. So we clicked up on that frame icon. Now I clicked on the load cell, and now you'll see we've got force, where we usually do the calibration. But we also have the checks button, where I can set up my periodic calibration and my balance drift check. So I think these are 2 features that aren't often used, but can be very handy for that rare occasion that something has happened. You'd really want to know about it sooner than later. And that's it for us. So just again to summarize, we went through the strain and displacement terminology in Bluehill. We compared how to look at different measurements using the graph is my primary go-to, but the raw data viewer is also useful just to see how different things are behaving at the same time. Setting up the transverse strain isn't as straightforward as axial, but it's just an extra step by looking at the specimen width. And then measurement pretest limits, setting those, transducer ranges, and finally data rate settings. And again, remember, you can find most of these answers in Bluehill help file. I know I did. And come back next month for the next webinar on Expression Builder. And I don't know if anyone has questions or if any questions have come in, but happy to answer those. Let's see, I'm just looking through some of the questions now. Looks like some of them have been answered. The question about balance, sorry, that was balancing means to return it to zero. So to balance a load cell, certainly with no grips on it and no load on the, no specimen in the grips as well. Yes, a deflectometer can be used as a strain source. Someone asked about measuring the uncertainty of a test with Instron load cells, extensometers. I don't know if we have anything defined or structured, but it's really just measuring kind of the uncertainty of, the same way you'd measure uncertainty for any other measurements. Really, it's just finding all the possible sources of error or uncertainty, and typically kind of that root mean square is I think the process most people would follow. Crosshead speed accuracy. So our different model frames would have different speeds sometimes of the crosshead speed. We do offer speed and displacement verifications. Depending on what standard you're following, whether it's ASTM or ISO, they're very similar, I believe. But as far as the accuracy, we would have a spec. It really depends on what model you're looking at. All the previous webinars are on instron.com. There's a resources section at the top of the website, and in there you'll see webinars going back last several years. Also, they're on our YouTube channel. You can find them as well. Some people ask about, there's one question about Poisson's ratio. So that is using, the axial and transverse strain. Really just having two sources for that, two measurements. Then we have a calculation for Poisson's ratio. It'll send out the ratio. If you want to see what the what the strains were that made up that ratio, you could report the individual measurements either at a single point, or you can set it up. You can put that entire measurement in your raw data viewer and see every point up to that point. You can also create a virtual measurement for Poisson's ratio to measure Poisson's ratio or calculate it at every data point if you wanted to, or at least the ratio between transverse and axial strain. And then you could even plot it as a graph because you would have a data point for that Poisson's ratio calculation at every data point. So that's where Expression Builder becomes very powerful. There's a question about when to balance the force. So you'd never want to balance the force when a specimen is gripped in both top and bottom grips, because that would be a real force applied to the specimen. Sometimes just gripping it would impart a compressive or tensile force on it. So you definitely want to avoid that. But if either no specimen is in the grips or it's only held by one grip at the moment you balance it, that's fine. You just don't want to balance the force after you've gripped both ends of the specimen. We do have in our preload, in the pretest section, you can preload a test, kind of pre-tension it just to get the specimen straight. We do have the ability to auto balance force. I don't recommend it. I think there was once in my career, it was a compressive test that it made sense to balance the force after preloading, but most of the time you don't want to, because that's a real force on the specimen that you're balancing out, and it's just going to essentially subtract it from the other end of the test, which most people don't want to do. So just be sure you understand what balancing the force would do to your application if you're going to do that. Looks like we have a question about what the data sources were on the graphs. We can go back to that in a moment. Some questions about seal force. I'm not sure if I can answer that well enough right here, but certainly if you want to send us a message, email, maybe we can get those answered for you. I will not be at the roadshow coming up. Some of my colleagues will be, and certainly they can answer all the questions for you as well. I don't know if there's any other questions, Ashley or Nick. If you see anything that I'm missing, let me know. Let's see if we. Yeah, so we'll pop back over to that other continue a test. So you can see we're in demonstration mode right now. I'm not connected to a live frame, but we've got some data that we ran. So for this graph too, if we click on the pencil over here, and now we can look at, so for example, my X data is set up for time because I know that's a constant for all the different measurements. This happens to be a multi-measurement graph, so I can only look at one specimen at a time, but I can look at all the measurements for that specimen. So for my Y data, I've selected displacement, tensile displacement, tensile strain, and digital strain 1 as to show on the graph. And so these are the sources for it. And if I close this, so again, this is the graph that we were talking about on the graph number 2 over here. I can click on method and go to my measurements. I can also go to workspace and go to graph 2. So there's multiple ways to get there. But if I go back to measurements, again, I can go through and see what my sources were. So for digital strain 1 axial, it was my digital strain 1 input, which goes through the same connector as digital strain 1 and 2 go through the same connector, but they're from, they're 2 different measurements. And then my tensile strain, I've set up my source to be digital strain 1. And so that's where it would start for the test until I remove it during the test, and then it'll be cross-head displacement. Strain can be balanced after the specimen has been installed. Yes, in fact, most of the time, if we look at under test control, pre-test, I probably should have shown this, apologize. So we've got preload, and in this case, I'm just going to 5 newtons at 10 millimeters a minute. And further down, we have auto balance enabled, and we've got available on the left, selected on the right. And so we're balancing our tensile strain, even though our source is digital strain 1, which you'll see it's on the left. We're not balancing the source, but we're balancing tensile strain, which fundamentally balances both. And then digital strain 2 is also being balanced. And so what that means is that we'll preload the specimen up to 5 newtons, and then we'll balance everything. So our tensile strain, our tensile displacements, our transverse strain will all start at 0 during the test. Can we draw a line limit on the graph section? I don't believe so. You can set up domains, which might be useful for you, but if you're looking for kind of a, a value that would tell you like pass fail or how close to this value you got. No, we don't do that here. We can do it in Bluehill Central, I believe, and some other more analytical post-process programs that we have for looking at your whole database, not just individual tests. And then someone asked about, yep, Bluehill has 5 types of yield calculations. So this can get pretty deep too. Not only yield calculations, but modulus. Some of them are historical, meaning before computers, we had chart paper and we'd draw a line and you'd count the boxes and, you know, what's the rise over run, that'll give you your modulus. And your yield or your offset yield would be based on that. So if we look at modulus, so our modulus, and then we've got a whole drop down. In fact, there's even a few more. If I'm in a tension method, if I was in a metals method, gives us a few more options for modulus. But you can see automatic Youngs, those are the more automatic ones in a sense that will do like a linear regression and tell you where the steepest portion of the curve was. And you have options of how to slice up that curve, where to look, where not to look. If you push F1 or go to help, it explains each one of these calculations in detail with graphs or drawings, and to really give you an idea of what each one does and what's best for your application. So segment would be between 2 points, chord, secant, tangent, all of those are from the days that you're going to put a ruler to paper, and it just makes it a lot easier to, you know, you're starting at 0 and going to some other value. It's easier to do the math essentially, but now that we can integrate, you know, area under a curve much easier with software and 5,000 points per second, it just makes it, most of those aren't really used anymore except for historical data. And then we've got E-modulus, which is the elastic modulus, and it's slightly different than automatic Youngs of how it works and what areas it looks for, the steepest area of that curve. So again, very similar, but if I go up to the help button, don't know what screen this is going to share on, but it should bring us to the calculations screen because we're in calculations. And now we can look for the library, let's say metals, and then we can go for okay, thought the modulus would be there. We'll go back here, go common, and then modulus. And now you can see we've got all different ones. Go to automatic Youngs, and image is kind of tiny, but the idea is that it shows you that when it divides the region of the slope, it divides it along the y-axis. One thing to just keep in mind is that this is where you would want to make sure you have enough data to divide it into those number of segments evenly. If you had 4 data points for your whole test and you divide it into 5 segments, that's not enough data. So just something to be aware of, what axis is being divided to look for the steepest range. And even that is optional in some cases of what measurement will be the source for that. And then getting to your question about yield. So again, you've got numerous types, 0 slopes, different thresholds, offsets, lower yields, proportional limit. The offset is probably the most common, and this would be a 0.2% offset. So it's essentially, even if I didn't have a modulus calculation enabled, which that's why it asks for a parent calculation, it's looking for, do you already have a modulus calculation? And then I will draw this offset yield line 0.2%, you know, to the right or offset from the modulus at the same slope. And then wherever this line crosses the curve, that is my offset yield point. And then I'll report the stress at offset yield. So again, going to the help file, we'll explain each one of these in detail. And I don't see any other questions coming in. So again, if anyone has other questions in the future, please feel free to reach out. Go to our road shows. We got a couple coming up, different parts of the world, and let us know if you have any questions.
All right, thanks, Dan. Before we wrap things up, I just have a few quick notes. First, for those questions not addressed live today, I do think Dan did get to them, most of them, but in case we didn't, I'm gonna send a list to Dan afterwards so he can address those. I'm also gonna be sending a copy of today's recording along with a slide deck to everybody here, so keep an eye out for that. And then I also want to make a plug. So Dan was obviously showing Bluehill Universal, but some people still may be on older versions of Bluehill. So if there's features or anything that you're interested in seeing more of, we do offer one-on-one demonstrations of the software. So you can sign up for those on our website on the Bluehill Universal product page. So I just recommend you check that out if you're interested. And then lastly, if you did like this session, we do have another event coming up later this month on the 22nd, and that's going to be covering some advanced capabilities in Bluehill Universal, working with variables. I believe Dan had mentioned this one at some point. So definitely, I'm going to be dropping a link into the chat now, where you can find a link to get reminded about that session, and then also all of our on-demand sessions that Dan had referenced throughout on some of the slides. That we have a lot of webinars from over the years available on there, so I definitely suggest you check them out. And then with that said, I just want to say thanks again for Dan for presenting. Great job. And thanks all of you for attending. Really appreciate you joining us, and we hope to see you again next time. Have a great day, everybody.